Jai Jagannath. So, welcome to lecture number 2 of chapter 25, that is current, resistance, and EMF. So, in the last class, we had derived a relation that is I is equal to NEA VD, where I is the current, VD is the drift velocity. Okay. So, today we will start a term with resistivity. What done by resistivity? Its symbol is rho. Now see, in the last class we had derived that current, current that is I, the rate of flow of charge, that is the flow of electrons, depends upon what? Electric field. So that means the I is proportional to E. That implied I can say if the current divided by area is also proportional to A. That implied what is I by A? It is nothing but current density, that is J. So J is directly proportional to the electric field intensity. Or you can say J is equal to some constant into E. So that constant is equal to 1 upon rho. That constant is equal to 1 by rho into E. Or I can write J is equal to E by rho. Or rho is equal to E by J. So this rho is called specific resistance. This rho is called specific resistance of a material, of a conductor, or it is called resistivity. Resistivity. This is called rho. Okay, so this rho, or we can say from this formula, you see J is equal to 1 by rho into E. So 1 by rho is also called sigma. 1 by rho is also called sigma. So here sigma is equal to 1 upon rho. That is reciprocal of resistivity. And this reciprocal of resistivity is called sigma, which is called conductivity. Conductivity. Or the reciprocal of resistivity or reciprocal of specific resistance is called specific conductance. Specific conductance. Now, so what is the unit of rho? What is the unit of rho? So if you find the unit of rho, so rho is equal to C E by G, E by J. So rho is equal to E by J. E is the electric field intensity, which is equal to volt per meter, divided by J. J is current density, that is ampere per meter square. That implied volt by ampere into meter square by meter, that is meter. So that is equal to volt by ampere is nothing but ohm, and this is meter. So ohm is expressed as, this is the symbol of ohm, meter. So this is the unit of rho. So generally the specific resistance of a copper is taken to be 1.72 into 10 to the power minus 8 ohm meter. This is the resistivity of copper material. Resistivity depends upon what? Resistivity depends on nature of material. Nature of material. If copper density, if the resistivity of copper is this much, resistivity of aluminum is different. So that can be found from the data table. So this is your resistivity. Okay. So now we will discuss what is the resistance. What is the resistance? For example, what is the resistance? So resistance symbol is R. Resistance symbol is R. So what is resistance? You see, before that you find what is the unit of sigma. What is the unit of sigma? Sigma is reciprocal of resistivity. That is called conductivity or specific conductance. So if the unit of rho is ohm meter, then I can say unit of specific conductance or conductivity is 1 by rho, that is 1 by ohm meter. So that is ohm inverse meter inverse. Okay, so yeah, so that is now come to resistance. So what is resistance? We know, suppose you take a conductor, this is a conductor, okay, and we are maintaining a potential difference of V across these two terminal of the conductor, and length of the conductor is say L, and due to this potential difference an electric field is developed in the conductor, so that is E. So now here we have discussed E is equal to, what is the relation between E and J? So E is equal to rho into J. But what is E? E is called electric field intensity, which is equal to negative potential gradient dV by dl. So here potential difference is V, length is L, so we can say E is equal to V by L. That is equal to rho J. J is equal to current density, that is I by A. Okay, so now we can write V is equal to rho into L by A whole into I. So now at constant temperature, rho is constant, length and area are also constant. So we can say rho L by A is constant for a particular temperature. So that constant is nothing but R. This rho L by A is called R. So V is equal to R into I. Where R is equal to rho L by A. So this R is called resistance. This R is called resistance of the conductor. Or you can say R is equal to V by I. R is equal to V by I. Since R and I, they are inversely proportional. That means we can say resistance opposes to flow of current. Actually, what is the meaning of resistance? What is the concept of resistance? So resistance means when you see when electric field is applied to a conductor, electrons will move opposite to the direction of the electric field. So when electron starts drifting from lower potential to higher potential, during their motion, they will collide with each other. And during collision, there is some energy loss. So since there is some loss of energy during the motion of the electron, we can say there must be some opposition by which there is some energy loss. So that energy loss is called resistance. Okay, so this is the concept of resistance. Now R is equal to V by I. So what is the unit of resistance? V is volt, I is ampere. So we can say unit of resistance is equal to ohm. So we got R is equal to rho L by A. Since at constant temperature, for a particular material, rho is constant. So for any type of material, rho is constant. That means for a particular material, rho is constant. If rho is constant, we can write resistance is directly proportional to the length and inversely proportional to the cross-sectional area of the conductor. So we can justify, you see, if length of a conductor increases, suppose this is a conductor, its length is L. Now I will increase the conductor length by 2 times. So if the length increases, what will happen? The number of collision of the electron will increase. If number of collision will increase, then there will be more loss. More loss means more opposition. So resistance will more. So resistance is directly proportional to length. And it is inversely proportional to the area of cross section. Suppose you see, this is a conductor. This is the area of cross section A. Now I will increase the conductor area by 2 times. So what will happen? So here the area is less. So less number of electrons per unit time will pass. So here if area increases, you see, if area increases, what will happen? More number of charge per second flow increases. That means rate of flow of charge will increase. That means current increases. That means if current will increase, definitely there is less opposition. So resistance will decrease. So resistance is inversely proportional to the area of cross section, or we can say R is proportional to L by A, or R is equal to some constant into L by A. This constant rho is called specific resistance or resistivity of the material. Okay. Now, what is Ohm's law? What is Ohm's law? You see, Ohm's law states that at constant temperature, rho is constant. At constant temperature, rho is constant. So if rho is constant, L is constant, length of the conductor is constant at constant temperature, because if you maintain temperature constant, length will remain constant. If temperature increases, it will expand, length will also increase. But at constant temperature, rho is constant, L is constant, area of cross section is also constant. That implied R is equal to rho L by A, that is constant. So if R is equal to constant, so we know the relation V is equal to R into I, we have proved, or I is equal to V by R. We have already seen this equation previously. So I is equal to V by R. So since 1 by R is constant, we can say 1 by R is also constant. So that implied I is proportional to V at what condition? At constant temperature condition. So this statement is your Ohm's law. This statement is Ohm's law. That is, current flowing through a conductor is directly proportional to potential difference across it. And what is the limitation? Limitation is that under which condition? Under constant temperature condition. So this is your Ohm's law. So always remember. So some may tell, sir, why not V is proportional to I? But I always tell I is proportional to V, because you see, current depends upon voltage. Voltage is the cause, current is the effect. So effect is proportional to cause. Just like income and salary. So salary depends upon income, not vice versa. So we can say salary is proportional to income, not reverse. Similarly, here current is proportional to voltage at a constant temperature, which is your Ohm's law. Next we will discuss the temperature dependence. Temperature dependence of resistivity and resistance. How the resistivity or resistance depends upon temperature. Okay. Suppose at T naught temperature, the resistance of the conductor is your R naught. So generally, the initial temperature is taken to be 20 degrees centigrade. So let at T naught temperature, that is 20 degrees centigrade, resistance is R naught. Now I increase the temperature from T naught to T. So let at T temperature, the resistance is equal to RT. So what is the change in resistance? Change in resistance is equal to what? RT minus R naught. What is the change in temperature? Change in temperature is equal to T minus T naught. And it is experimentally proved that change in resistance is directly proportional to the initial resistance. And change in resistance is directly proportional to rise in temperature or change in temperature. Or we can say the change in resistance is proportional to initial resistance as well as proportional to rise in change in temperature. Change in temperature is final temperature minus initial temperature. Or we can write the del R, change in resistance, is equal to some proportionality constant into this. So that proportionality constant is taken to be alpha. So alpha R naught into T minus T naught. So that implied alpha is nothing but the change in resistance by R naught into T minus T naught. Then what is alpha? Alpha is called temperature coefficient, temperature coefficient of resistance, temperature coefficient of resistance. This is called alpha. Then what is the unit of alpha? Unit of alpha is here in the numerator resistance, that is ohm, in denominator resistance ohm cancel. So in the denominator you are getting change in temperature either in degree centigrade or Kelvin. So we can write unit of alpha is 1 by temperature, that is degree centigrade inverse or Kelvin inverse. So we can write here what is del R? It is nothing but RT minus R naught, which is equal to alpha into R naught into T minus T naught. That implied RT is equal to, bring R naught here, take common R naught. So R naught into 1 plus alpha into T minus T naught. So this is the resistance value at any temperature with resistance at initial temperature. So now we can say resistance depends upon what? Resistance depends upon three factors. One is initially what was the resistance. Then it depends upon rise in or change in temperature. Rise or fall, no problem. So it is depends upon change in the temperature. Also it depends upon alpha. Alpha depends upon nature of material. Nature of material. So according to that, the resistance varies with respect to temperature. So this is the resistance, how it depends upon the temperature. So now similar to this, we can say there is also change in resistivity of a material with respect to temperature. Same thing we can write here, the resistivity at T temperature is equal to resistivity at T naught temperature into 1 plus alpha into T minus T naught. So this is the relationship between resistivity at T temperature with resistivity at 0 T naught temperature. And so now you see, then what is the value of alpha? What is the value of alpha? We can see alpha value is positive for a conducting material. For a conductor, we can say alpha is positive. So that means we know what is RT. RT is equal to R naught 1 plus alpha into T minus T naught. So here, as temperature increases, what will happen to T minus T naught? T minus T naught is positive. Alpha is also positive. So that means we see RT is equal to R naught, multiply this R naught plus alpha into R naught into T minus T naught. So for a conducting material, for a conductor, alpha is positive. If alpha is positive and you are rising the temperature, so T minus T naught is also positive. So everything is positive. So we can say RT is greater than R naught. That implied for a conductor, if temperature increases, If temperature increases, the resistance also increases, and vice versa. That means if temperature decreases, resistance decreases. This is applicable for conductor. So conductor means, what is the example of conductor? Silver, gold, copper, so etc. So for this, alpha is positive, and for that means if this is the temperature in Kelvin and this is rho or resistance. So here with increase in temperature, resistance increases. So this is for which material? For conductor. Now come to semiconductor. For semiconductor. So what is the example of semiconductor? Germanium, arsenic, gallium arsenide. So like this, here alpha is negative. Alpha negative means what? Alpha negative means if temperature, you see, if temperature increases, alpha is negative, so RT is equal to R naught minus something, because alpha is negative. That implied if temperature increases, resistance decreases. So this is for which case? For semiconductor, and vice versa. Vice versa means if temperature decreases, resistance increases. This is for semiconductor. Just like you see, if temperature will increase, the resistivity or resistance will decrease. So this is the graph of resistivity or resistance versus temperature for semiconductor. Okay. Then another is for some alloys like nichrome, manganese, and constantan. So in this type of material, what happens? As temperature increases, the resistance and resistivity does not change. Resistance or resistivity do not change. That implied alpha is equal to 0. If alpha is equal to 0, we can say RT is equal to R naught. That means resistance or resistivity remains constant for which type of material? For some specific alloys like nichrome, manganese, and constantan. So here, that means if you draw a graph between rho or resistance versus temperature, the graph is like this. So here resistance almost remain constant. That is why we are using nichrome. So, tungsten also same. We use tungsten. So here we can add here tungsten. So we are using tungsten in the electric bulb, because you see, if the bulb will run for some times, so heat energy will be produced due to Joule's law of heating effect, I square RT. So due to that, the resistance should increase. If resistance will increase, then current will gradually decrease. So that means the bulb will not give the required illumination. So that is why we should design the filament in such a way that the resistance should remain constant and it should be independent of the temperature. For that cause, we are using the tungsten in the electric bulb. Now, what is your superconductor? What is superconductor? Okay. So for some materials, including several metallic alloys, metallic alloys and some oxides, metallic oxides, what happened? As temperature decreases, as temperature decreases, resistivity decreases. We know for metallic conductor, if temperature increases, resistivity increases. But as temperature decreases, resistivity decreases. But if we will decrease the temperature to a certain value, below that value, resistivity totally be zero. That means at a particular temperature, at a particular temperature, that is called critical temperature. That is called critical temperature, where resistivity will be suddenly reduced to zero. That means if we draw the graph resistivity versus temperature, if we increase the temperature, resistivity increases. If the temperature decreases, then resistivity decreases. So at a particular temperature, that is Tc, resistivity will be zero. If resistivity will be zero, there is no opposition. There is no opposition. So whatever current is there, it will continue. Even if you will disconnect the supply, the current will continuously flow. That means it will behave as a superconductor. So at a particular temperature, critical temperature rho will be zero. So below this critical temperature, the conductor behaves as superconductor. Behaves as superconductor. Okay, so this is about here. This is about the various characteristic of conductor, semiconductor, and some alloys and some superconductor. So now we will see what do you mean by ohmic conductor. What do you mean by ohmic conductor? So ohmic conductor means it is a conductor which obeys Ohm's law. Which obeys Ohm's law. What is Ohm's law? Ohm's law states just current is directly proportional to potential difference at constant temperature. So now if we draw a graph, then the current versus voltage graph is a straight line. So this is called ohmic conductor. What is the example of ohmic conductor? Silver, gold, aluminum, etc. These are called ohmic conductor. And if this current voltage graph makes theta angle, then by measuring this slope, we can find the resistance value. You see, in the numerator, it is I. In denominator, it is V. So if I will take I by V, then it will be tan theta. But I by V is nothing but 1 by R. So 1 by R is equal to tan theta. Or you can say R is equal to cot theta. So by measuring the theta angle and taking the cot of this function angle, we can find the resistance. Suppose this is the voltage, this is the current graph. If for ohmic conductor, it is the voltage current graph is a straight line. Let us say it is making theta angle with the current axis. So here ordinate is voltage, abscissa is current. So the ratio is your tan theta is equal to V by I, which is equal to R. So resistance can be found by measuring the slope. Tan theta is nothing but slope of VI characteristic. So in this way you can measure. Then what is non-ohmic conductor? What is non-ohmic conductor? The conductor which does not obey Ohm's law. That is, I is not directly proportional to V. So that type of conductor is called non-ohmic conductor. So here, if you draw the current versus voltage graph, so it is not straight line, rather it is a curve like this. Okay. So I think you have in electronics, you have read the diode characteristic. So this is current, this is voltage. So this characteristic is not straight line. So this is the characteristic current versus voltage graph of a diode. So diode is a non-ohmic conductor. Okay. So now the ohmic conductor, the another example of non-ohmic conductor is solution of S2SO4. Hydrogen sulfate solution is a non-ohmic conductor. Now, what is the dimensional formula? Dimensional formula of resistance. So, R is equal to what? V by I. V is equal to what? Amount of work done by bringing a unit charge, that is W by Q. And this is your I, that is equal to W by Q. Q is equal to IT, this I. So, that is equal to I square time. Work done dimensional formula is ml square T minus 2 divided by I you can take it is A square into time is T. So, that is equal to m L square T minus 3 A minus 2. So, this is the dimensional formula of resistance. Okay. Then, what is the dimensional formula of resistivity? Rho. So, you know R is equal to rho into L by A. That implied rho is equal to R into A by L. So, we have already known the dimensional formula of R. M L square T minus 3 A minus 2 into area is length square divided by length. Only you will get L. So, here L square, here L. So, if you multiply, you will get LQ. So, this is the dimensional formula of rho. In this way, you can find the dimensional formula of sigma. Sigma is reciprocal of rho. Rho dimensional formula is this. Just take the reciprocal. So, M minus 1, L minus 3, T Q A square. This is the dimensional formula of thick. So, this is the dimensional formula of sigma. Then, what is conductance? What is conductance? Conductance symbol is G. It is the reciprocal of resistance. Reciprocal of resistance is conductance. You know the dimensional formula of resistance. Just take the reciprocal of R, you will get G. So, dimensional formula of G is equal to resistance is this. Take the reciprocal M minus 1, L minus 2, T Q A square. This is the dimensional formula of G. Now, see, suppose this is a conductor. This is a conductor whose length is L, area of cross section is A. Here resistivity is rho. Suppose this is a copper. Now you take same area of cross section but take the double length as compared to this. But this is also same copper material. Here I want to find what is the resistivity of this material. So, can anybody answer? Okay. So, this is the area is A, length is L. Here same area but length is double and same material. Then what is the resistivity here? Resistivity does not depend upon the dimension of the conductor. It depends upon the copper, nature of material. Since nature of material is same, so here resistivity is also same. But if the resistance of this conductor is R, then what is the resistance of this? Here you see, area of cross section same. Rho of both are same because same material, but length is doubled. If length is doubled, resistance will be doubled because you know R is equal to rho L by A. So here rho and A for both are same, but length is double here, so resistance will be double. Okay. So this is an example. Here resistance of copper at 20 degree centigrade is given 1.05 ohm. We have to find what is its value at 0 degree centigrade and what is its value at 100 degree centigrade. So we had got a relation RT is equal to R naught into 1 plus alpha into T minus T naught. This is according to the theory. So here this resistance, what is the resistance given at 20 degree centigrade? It is 1.05. So we can say we can say the resistance at 20 degrees centigrade given is equal to what? 1.05 ohm. So that means this is the initial resistance. This is the initial resistance R naught, which is equal to R20, which is 1.05 degrees 0.5 ohm. We have to calculate what is the resistance at 0 degree centigrade. So that means the final temperature is 0 degree centigrade. This is the initial temperature. 20 degree centigrade is, we are taking the reference, this 20 degree centigrade is the initial resistance. We have to find what is the resistance at 0 degree centigrade. So what can I write? Here I can write RT. T is equal to what? 0. So R0 is equal to R20. So here we are taking the reference. Reference is 20. So R20 into 1 plus alpha. Final temperature is 0 minus initial temperature is 20. So this is the value. So that implied R naught is equal to, what is R20? It is 1.05 whole into 1 plus alpha 0.00393, that is given in the data sheet. So 0 minus 20. So just multiply this, you will get R0, that is resistance at 0 degree centigrade. You will get the value 0.97 ohm. Okay. So this is at what temperature? T is equal to 0 degree centigrade. Now we will find what is the resistance at 100 degree centigrade. So that means the resistance at 100 degree centigrade, R100, is equal to, initial resistance is given R20 into 1 plus alpha into final temperature minus initial temperature. Final temperature is 100 minus initial temperature is 20. So that is equal to, R20 is given what? 1.05 into 1 plus alpha 0.00393 into 100 minus 20, that is 80. So if you will calculate, I think it will come 1.38 ohm. Now see, at 0 degree centigrade, just analyze this problem. At 0 degree centigrade, what is the resistance value? Resistance value is 0.97 ohm. At 0 degree centigrade, resistance is 0.97. At 100 degree centigrade, what is the resistance? Resistance is 1.38 ohm. Okay. So now you see the difference. So that means resistance at 100 degree centigrade divided by resistance at 0 degree centigrade is equal to 1.38 divided by 0.97. If you calculate, it is 1.42. That means if temperature increases by 100 minus 0, that is 100 degree centigrade, then resistance increases by, so new resistance is 1.42 of R naught minus R naught. That is, the change in resistance is 1.42 R naught. This is your R100 minus initial resistance is R naught divided by the initial resistance into 100. We are calculating the percentage change in resistance. So it is about 42%. So by increasing the temperature from 0 to 100 degree centigrade, resistance value increases by 42%, which is not tolerable for a design engineer. Okay, that means what is Ohm's law? Ohm's law says V is equal to IR. You see, if temperature increase by 100%, resistance increases by 42%. So if resistance increases by 42%, then to maintain same current, you see, resistance increases by 42%. So to maintain same current, I have to increase the voltage by 42%. So then to maintain same current, voltage must be increased by what times? 42%. But increase of voltage is not in our hand. But we can design the resistance in such a manner that that with increase in temperature, resistance should not increase with great amount. Okay, so accordingly that we have to design the proper conducting material. So that is the part of a design engineer. Now see, this is test or understanding 25.3. Question is, if V is doubled, the current in the wire increases by what factor? Does it increase? If it will increase by 2 times, greater than 2 times, less than 2 times. Now see, if resistance remains constant, then current is directly proportional to voltage. We know according to Ohm's law. Okay, so if V is doubled, then automatically current will be doubled. Provided the resistance is constant. So in this case, if resistance is constant, we can say current increases by 2 times. So this would be the answer. First bit would be the answer. But here it is told that if V is doubled, what will happen? If voltage is doubled, if voltage increases, definitely current will increase. If current will increase, what will happen to the I square RT? I square RT will increase. I square RT is nothing but heat produced. So heat produced will increase. If heat produced will increase, what will happen to the temperature? Temperature will increase. If temperature will increase, what will happen to the resistance? Resistance will increase. So resistance will not remain constant. So that means whatever resistance was there, now resistance will increase. So what is current? Current is equal to V by R. Okay, current is equal to V by R. Let us say I have taken. Now see, I is equal to V by R, we know. So now voltage is doubled. So voltage is now 2 times of V. So here resistance is not constant because resistance increases due to increase in the temperature. So let us say new resistance is 1.1 R. So if we calculate 2 by 1.1, it is 1.81 V. It is not equal to 2 times V. So here current increases. Current increases by what times? 1.81, which is less than 2. So which answer is correct? This answer is correct. Now see, suppose this is a conductor. Okay. So here length is L, area of cross section A, rho is the specific resistance. I will stretch this conductor. I will extend this conductor. That means length is now increased. Okay, length is increased by what times? Let us say n L times. So this length may be 2 times of L, 1.5 times of L. So however, the length increases. But you see, if length increases, definitely the area will decrease. Because what is the concept? Concept is that the total volume of the material will remain constant. So by stretching, if length increases, area will decrease. So by compressing, if I compress this conductor, then what will happen? By compressing, the area will increase and length will decrease. So let us say length is equal to new length, L dash is equal to n times L. So here n is less than 1. Okay. So whether you are stretching the length or compressing the length, in every case the area will change. But if area will change, definitely resistance will change. So let us say here resistance is R, here resistance is R dash. So what is the relation between R dash with R? Okay, so that means if a conductor, okay, so I am writing here, you can write, if a conductor is stretched or compressed, to n times, then volume will be remain constant. You are not going to change the volume. Volume remains constant but only changing the length. If length changes, area also changes. Since volume remains constant, what is the initial volume? Area into length. This area into length is the volume. New volume is equal to what? New area is A dash. New length is L dash. Okay. So that implied A dash into L dash. So you are compressing or extending to length by n times. So new length is equal to NL times. So from this we can say this L cancel. So A dash is equal to what? A by N. A by N. Then what is the new resistance? R dash is equal to rho L dash by A dash. That is equal to rho. What is L dash? L dash is equal to NL. What is A dash? A dash is equal to A by N. This N. That is equal to N square rho L by A. But what is rho L by A? It is nothing but the initial resistance. So here resistance is equal to what? Rho L by A. So N square R. So we can write R dash new resistance is N square time old resistance. Okay. So let us solve a problem. If you solve a problem, suppose one question is given. A wire is compressed. A wire of resistance. A wire of resistance, let us say 10 ohm, is compressed to half of its length. Then new resistance will be, option is given 2.5 ohm, 5 ohm, 10 ohm, then 20 ohm. So which is correct? You see, so here resistance was 10 ohm. It is compressed to half of its length. That means N is equal to half. If N is equal to half, then new resistance according to this formula, it is N square R. That is half square is equal to 1 by 4. That initial resistance is given 10. 10 by 4 is equal to 2.5 ohm. First, whether you will see whether it will decrease or increase. Definitely it will decrease, because length decreases means resistance will decrease. And since length is decreasing, area will increase. And we know R is directly proportional to length and inversely proportional to the area. If length decreases, resistance decreases. If area increases, resistance will decrease. So definitely resistance will decrease, but by what factor? N square, that is 2.5 ohm. So this is a question. Suppose this is a conducting body. Here we have to find the resistance between first and second surface. Okay. Suppose you will connect a battery source here between 1 and 2. So here the current, when current will pass, it will see the resistance across this first surface and second surface. So what is the resistance between first and second surface? You know, suppose the specific resistance of this material is given rho. So R is equal to rho L by A. So that is equal to rho. What is the length? From 1 to 2 surface, what is the length? Length is C, divided by, what is the area of cross section? This is the area of the cross section. So that is this length is A and this length is B. So A into B is the area. So this is the resistance between 1 and 2. Similarly, so rho into C by this. I want to find resistance across 3 and 4 surface. So if I will connect a battery from third surface to fourth surface, then the current will see the resistance between third and fourth surface. In that case, what is the resistance? Resistance is equal to rho into from third surface to fourth surface, what is the length? Length is equal to B, divided by what is the area of cross section of the third surface. For third surface, area of cross section is A into C. So this is the resistance of third to 3 to 4 surface. Similarly, resistance between fifth and sixth surface, that side, back side, and this front side. So what is the length? This is A is the length. And what is the area? This is B, this is C. So area is BC. So R is equal to rho. The length is A divided by BC. So this is the resistance. Now, this is very important for particularly engineering student. Color coding of carbon resistor. Okay. So you see, generally in commercially in the market, we can get the resistance of what? Nichrome, tungsten. So these type of resistance are available in the market, that is manganese. So what is the advantage of this? Here resistance does not depend upon temperature. Almost resistance remains constant. But there is some limitation, because for suppose we will use the resistance whose value we need more in terms of mega ohm, kilo ohm, like that. In that case, we should not take this resistance which is available in the market. So now for that we have to take the carbon resistor. The carbon resistor are very small size and they are very compact. That is, carbon resistor are very small. So we cannot write the resistance value on this small size carbon resistor. So for that we have to use the color coding. You see, so there are 4 band of the colors are given in the carbon resistor. 1, 2, 3, 4. So first color, the first and second number, this first color band and second color band, that is 1, 2, represents the number. Okay. Third band, that color represents the multiplier of 10, 10 to the power 0 or 10 to the power 1 or 10 to the power 2, like that. And this fourth band color gives the tolerance value. Up to what value you can get the resistance. Resistance can, the value of resistance is more than what, or within what range the resistance will remain. So that is the fourth band. For example, you see, so for black color, the first color band and second color band, if it is black, then it is taken to be 0. And if in the third band there is black color, then we have to take the multiplier factor of 10 to the power 0. Okay. Similarly, suppose we will take yellow. First band is yellow. That means we have to take the number 4. And if the second band is also second band is red, then we have to take the red as 2. And depending upon the color, we have to take the multiplying factor and first and second digit number and their tolerance. Let us take an example. Suppose this is a carbon resistor. First band of the color is orange. First band of the color is orange. So orange means, you see from this table, so first digit will be 3. So this orange color indicates 3. Then the second band of the color is yellow color. So yellow, you see, so yellow number is 4. So you write down 4, 34. And third color is blue. You see, third number will give the multiplying factor. So here blue color, you see the blue. So this blue color, what is the multiplying factor? 10 to the power 6. So you write down 10 to the power 6. So this is the resistance in terms of ohm. So this is the resistance of this carbon resistor. That is 34 10 to the power 6 ohm. That implied it is 34 mega ohm. And what is the tolerance value? Tolerance value means the resistance may be more than this or less than this by what percentage. Here you see fourth color band is given gold. This fourth number we will give the tolerance value. Since it is gold, what is the percentage of gold tolerance? That is 5%. So this is the resistance of this carbon resistor. Come to here. So in this case, first number is gray. You see gray. Where is gray? Gray is 8. So first number is 8. Then second number is red. Second number red. Red means 2. So you take second number 2. Then third digit, third band of the color will give multiplier. So here it is orange. Orange means 10 to the power 3 into 10 to the power 3. And this is last digit, that is fourth, is tolerance value. So silver, it is silver. Silver is plus or minus 10%. So here the resistance of this resistor is equal to 82 into 10 to the power 3 ohm, that is kilo ohm, plus or minus 10%. Okay, how will you remember? You see, I have taken a formula, it is commonly known to everybody, that is B.B. Roy of Great Britain has very good wife. So first is B, you see, first black, that is 0. And B.B. Roy, B stands for brown. Brown, for brown it is 1. The Roy, R stands for red. Red figure is 2. Then O is orange. Orange figure is 3. Y is yellow. Yellow is 4. Great Britain, that is G. G stands for 5. That is G stands for green. Green is 5. Britain, B is your blue. Blue is 6. Has very good wife. V is violet. Violet is 7. G is 8. Gray 8. Then wife, W is white. So in this way, you have to remember this. Okay. So now I have given first, you see. So this is a homework for you. This is 1. So first number is your black. Okay. Second is your blue. So this is your blue. Third one is red. This is red. And fourth is no color. So now this is a homework. You will write what is the resistance of this carbon resistor. So I think everybody, after solving this, just put your answer in the comment box. Okay, thank you.